So when we ended, we have the torque. The applied torque is going to be equal to tau at c divided by c multiplied by the integral over the area of rho squared times dA. So I had asked the question, does this look at all familiar to you? So remember, we've got a concept that we learned in our statics class that if we just simply integrate dA over the area, we get the area. If we have a rho dA, that is called the first moment of the area. If we have a rho squared dA, that is called the second moment of the area. And you guys did this. And this is actually called J. Some people use I sub P. I don't really care for that. But J is called the polar moment of inertia. So J is equal to the polar moment of inertia. And it is it depends only on the cross section of our circle. So the J term, we'll come back to that shortly to make sure that you remember how to calculate that. But that's something that we're going to kind of commit to memory. But now notice what happens. Now we've got that the applied torque is equal to tau at c divided by c multiplied by J. Well, now here's what's kind of cool. So this is the other part of the trick. Remember that tau of c was to c as tau at rho was to rho. We had that a little bit earlier. We actually had the rho upstairs over there. So now what we can do is I can replace the ratio of tau of c over c, and I can replace it with tau at rho divided by rho. So that's going to be equal to tau at rho divided by rho times J. And lo and behold, we have the shear stress at any radius is equal to the applied torque multiplied by the radial distance J, all divided by the polar moment of inertia. So now this is known because we get to pick it, and that's a known function of the cross section. So now we finally have the variable that we're interested in, which is the shear stress over that particular segment. Now what we typically do is we drop the rho because it's implied. In other words, we just assume that we're calculating it at some radial distance. And we have our next formula that we're going to memorize, which is tau is equal to T times rho divided by J. Very, very famous. Very famous. We'll put an exclamation point. And we also want to memorize this. T rho divided by J. Now, let's go back for just a second and remind ourselves what J is. What is J? Now, it turns out that it really doesn't matter the kinematics that we did for this particular problem. That could have been for a solid circle or it could be for a hollow circle. It doesn't make any difference. So what we're going to do is let's go ahead and write that J is equal to the integral over the area of rho squared dA. But now, and then let's assume that it can either be for a solid section or hollow. Let's go ahead and write it like this. So I'm going to write 2 radii, rho inner and rho outer. So now when I integrate over the area, that means I have to go from 0 to 2 pi in the theta direction, and I have to go from the inner radius to the outer radius. And then I have the rho squared times dA, which is rho d theta. Again, if you did not do this in your statics class, first off, I'm probably not going to believe you. But secondly, for shame, not on you, on your teacher, but I'm sure you did this because it's critical that you've had some exposure to this. So now we split this up. This is the rho direction, and the d theta is in the theta direction. So the theta one is easy. That's just going to be 2 pi. And then we have rho cubed, so that's going to be rho to the 4th divided by 4. And we're going to evaluate that from the outer radius to the inner radius. So that's going to give us pi over 2 times rho outer to the 4th minus rho inner to the 4th. Now, that would be fine to do, but what we're going to do instead is we are going to double, or pardon me, we're going to take the outer radius as half of the outer diameter. The inner radius is going to be half of the inner diameter. So we're going to take those values. So notice if I do that, 1/2 to the 4th power is 1/16. So this statement becomes that J is 1/16 times 1/2. So that's going to be pi over 32 times D outer to the 4th minus D inner to the 4th. Hopefully you've got memory bells going off madly in your brain, because this is very, very important for you to know. So I want you to memorize this one also. Now notice we chose diameter other than radius. Even though we did a lot of our analysis using the radius, we're going ahead and using the diameter instead. Why is that? So why D, not the radius? Because you probably know this. If you walk into Home Depot and you ask them, could I have a wooden dowel that has a radius of 1/2 inch, they'll say, oh, you mean a 1-inch diameter. So almost all sections are all in diameter. Nobody says this cylindrical section has a radius of such and such. So it's good for you to kind of go ahead and go with the flow on that. And we're always going to be using then the diameter when we calculate it. So even though we have T rho over J, for the polar moment of inertia, we'll always use the diameter section. So let's go back then to our famous formula. We have the shear stress is equal to torque times rho divided by J. Notice a couple of things. First off, that it is linear. So I'm going to double bullet this. It is linear in the radial distance. There it is. Rho is just sitting right there. So we've got that aspect of it. Also notice the force is upstairs. The T is in the numerator. That didn't come out very well. You know what I'm saying. T is in the numerator. It's upstairs. And then J is in the denominator. I'll abbreviate it so I don't have the same problem. Remember that earlier we have sigma is P over A. We have forcing function is upstairs. The cross-sectional property of the section is downstairs. Same thing. We've got forcing function up, cross-sectional property down, but now we add in the fact that the stress is going to be linear. So there's a slight change from the axial bar, but it has a lot of the same character that we had earlier. Now remember, we've got the dimensions of these things that have to match. We already know that tau is force per length squared. On the right-hand side, we have torque. That's going to be force times length, times rho, which is length, all divided by the second moment of the area. Area is L squared. Second moment means another L squared, so that's going to be L to the 4th. And that's going to be force per length squared. So that kind of helps us remember then what our sections are going, or pardon me, what our dimensions are going to be in case we ever need to go back and look at those particular formulas. The way that we normally visualize, again, we've already sketched what the radial distribution looks like, but again, in pictures, what does it look like? Here is typically how we would plot it. So for a solid cylinder, what we almost always do is we draw a radial line like this, and then we draw a linear slope like so. And I'm going to draw the magnitude of the shear stress like this. So that would be a plot of tau over the radius for a solid section. So tau for a solid section. That's what T rho over J would look like, because the rho we have is going to give us that linear variation. What if it's hollow? Well, if it's hollow, what we would do is the following. I'd make it like so. I draw a radial line like this. I would draw another linear, and I would go ahead and draw it on the outside, and then I would draw another one on the inside, and then I would fill in this, like so. There's nothing in here. This is air. So I don't draw a distribution on the inner part of it. So now I just have a tau for a hollow section. So the tau for the hollow section looks like it's linear. So it's linear over this part, but then it's 0, and there's nothing there over that particular segment. Now, a little bit later, we're going to do composite sections, and we're going to have to modify this slightly. But these are very common ways of plotting these particular stresses. So that would be the maximum. Tau max for a solid section is at the outer radius. Same thing here. This is tau max for a hollow section. That's going to be at the outer section of the radius as well. All right, so now we are set. We have our end result. One more time, tau is equal to T rho over J. That goes on your sticky note. I hope that you remember that formula until the day you die, which will hopefully be a very, very long time from now. But that's a formula you've got to have committed in your head. It's being used thousands of times as we speak, and we need to be able to understand it, and we're going to have a chance to practice it, but we are going to pick that up next time. We were heavy on the theory this time. We did a lot of analytical work. If you could follow through even 60-70%, that's terrific. And if you had it even at a higher percentage, that's tremendous. But we went from displacement to shear strain to shear stress to the applied torque, and we learned some new things on the way, and it got us to our final big result. And that closes us out for this lecture. See you next time.